Good afternoon, everybody. Welcome to the third part in the module on testing of concrete. If you recall, the first two lectures talked about fresh properties and then hardened properties. In terms of fresh properties, we took a look at typical workability measurements, and we followed that up with an understanding of the rheology of the concrete. And then we got on to discussing different aspects of testing of concrete, primarily the compressive strength, the flexural strength, the modulus of elasticity, and we also had a brief discussion about how we can get the complete stress strain response of concrete. As I was telling you earlier, the stress strain response is becoming increasingly important to understand the properties of special concretes such as fiber reinforced concrete, because there you can really design for concrete structures to be quite durable and ductile, and that is the primary emphasis on determining the stress strain response, is to estimate the ductility of the concrete. Okay. Now I know that there were some questions that people may have had at the end of the last session, so I suggest that before we begin today's session, if there are one or two quick questions pertaining to the content that was discussed in the first two lectures, this will also serve as a way of refreshing people's memory. So if you have specific questions about the first two lectures, we can have a brief interaction to begin with, and then I'll get on to the subject of today's lecture, that's going to be on testing for durability of concrete. Okay. So very quickly, if you have questions, let's try and interact first and get them sorted out before we move on to durability. Okay, just for the record, I'll once again state what we had actually discussed. We first started off with workability, then we got on to understanding the rheology of concrete and how it's important from the context of understanding special concretes like self-compacting concrete. We then discussed a little bit about how we can monitor the strength development of concrete using maturity method, and also some aspects of ultrasonic method to determine the strength development. Then we started discussing about compressive strength and what type of factors during the test affect the compressive strength measurement of the concrete. We discussed about different methodologies for estimating the tensile strength. We then talked about models of elasticity, and finally the full stress strain response. Okay. So if you have specific questions in this, please do ask at this time, because the content that we are going to be discussing today is quite different from what we discussed in the first two classes. So it may be better that we sort out those issues in the beginning itself and then move on to understanding of durability of concrete and how it is tested. We will start off with today's content, and then if you still have any questions about the first two lectures, then we can get back to them at a later stage also. Okay. For now, we will move on to today's presentation. Okay. So as I was telling you, today we will talk primarily about durability of concrete. Okay. So first of all, let's try and understand what is meant by durability and what are the different durability problems that we have in concrete. Now durability, you know very well, is the performance related characteristic of any material or structure. In terms of concrete, durability simply means how is concrete able to resist the actions of the environment in which the structure is servicing. Okay, for example, you have the marine environment where seawater can damage the concrete. So what are the different damages that occur to concrete, and how does concrete withstand that damage? What are the characteristics of concrete that make it withstand that damage? Can we measure those characteristics? Okay. So primarily, as far as durability problems in concrete are concerned, the primary problems that we deal with on a regular basis, the biggest problem of all is the corrosion of steel in reinforced concrete. And this corrosion itself is further subdivided into two types. One is chloride induced corrosion, that is the corrosion that happens in coastal environments wherever there is chlorides in the atmosphere or directly from the seawater. And then you have carbonation induced corrosion. Carbonation is a phenomenon that happens more inland, and that is basically the attack of concrete by carbon dioxide. So carbonation induced corrosion and chloride induced corrosion are two major aspects causing corrosion of reinforcing steel in concrete. The other common durability problems include sulfate and other chemical attack. For example, sulfate which is coming from groundwater, or you can have some chemicals like acids that are effluents from different chemical industries that may come in contact with different types of concrete. Sometimes you may even have chemical attack happening in pipes that is carrying sewage, concrete pipes that is carrying sewage. Even that can generate acidic conditions inside the pipe, and that acid can actually attack the concrete and deteriorate its properties. Okay. Apart from these common phenomena, you also sometimes work with aggregate that may be reactive. in the alkaline environment of the concrete and may generate expansions leading to cracking in the long term. That is called alkali aggregate reaction, and specifically in cold countries there may be sufficiently large variations of the temperature from sub freezing to above freezing, and that can cause freezing and thawing damage, which is basically related to the freezing of water to form ice, which leads to expansion and subsequent contraction to again form water from the ice. So we have this expansion and contraction cycles, which ultimately leads to the deterioration in the concrete or cracking in the concrete. Okay. So these are common durability problems. There are many more different types of problems that may be more typical to a very specific environment. I am not here to discuss all of those. Idea is to just give a brief glimpse before we understand how these properties can actually be measured. Now if you really look at a typical section through a reinforced concrete member, for example, if you consider a reinforced concrete column and take a cross section through that column, you will see that you have the main reinforcement bars and you have the tie bars which are tying up these main reinforcement. Okay. Now if you consider the concrete to be divided into two components, one which is outside of the reinforcing bars and one which is inside of the reinforcing bars, we can give these two different names. Okay. The concrete that is inside of the reinforcing bars can be called as heartcrete. Inside of the reinforcing bars we call it as heartcrete. Okay. That means that is the heart of the concrete. Now what is outside of the steel bars is in the cover zone, so that is why we give it a name as covercrete. Okay. So now if you really think about it hard, the part of the concrete that protects it from the external environment is essentially the cover concrete. So while the bulk of your concrete that is inside the reinforcement is responsible for the strength of the concrete column, the concrete column will be made durable or resistant to its surface environment only by the action of the cover concrete. So the cover concrete is what is responsible for the durability. That much you need to really understand, and especially other aspects of concrete construction such as curing obviously are done with an intention of providing a good quality cover concrete. Please remember, curing is very important for strength development, yes, but even more important for enhancement of durability of the concrete. So without curing you do not get good durability of the concrete in the cover zone. So now why do durability problems happen in concrete? Okay, we know that concrete is a very versatile, very durable, hard material. How does it degrade in a given environment? So let us take a look at, first of all, concrete is a multi-phase material. Okay, it has got different phases that have very different characteristics. We discussed some of this in terms of the impact on how cracking propagates within concrete. If you remember our discussion in the compression test, we saw that first the cracks are formed in the interfacial zone, then these cracks propagate through the matrix and finally form a large network. Okay. So heterogeneity of concrete is one of the primary reasons why concrete is weak in tension and is also poor when it comes to durability in certain environments. Okay. What are the different phases that you find in concrete? Of course you have the hydrated cement paste phase, that is essentially the cement and water that have reacted together. Then you have the aggregate phase. For the most part the aggregate phase is inert, unless you have very special types of aggregate that are reactive. Okay. For example, if you choose a volcanic rock as an aggregate, definitely it is going to be highly reactive in the alkaline medium of concrete. But most importantly in concrete you have this third phase which we call as interfacial transition zone. Now what is ITZ? This is basically the zone of bonding between paste and aggregate. Please recall when I talked about compressive strength testing, I said that for normal ordinary grade concrete, when you actually break the concrete in compression, the cracks tend to go around the aggregate, okay, not exactly through the aggregate but around the aggregate, and that is happening because your failure is propagating through the interfacial transition zone. Okay, so you have a multi-phase nature of concrete. Now why is it responsible for durability problems? Okay, why? Because it also has other aspects within it. For example, you have porosity in the system. These pores are mostly interconnected. Okay, pores are mostly interconnected. You also get air voids in the system which are generally entrapped because of the method of mixing of your concrete itself. Okay, so you have air voids, you have porosity in addition to the multi-phase nature of your concrete, and this porosity in a number of cases can lead to permeability. Now what is permeability? Permeability is the ease with which a fluid can pass through a solid. Okay, it is the property of a solid which governs the ease with which any fluid can pass through it. Just to give you an example, consider these two systems A and B. Okay, so you know that in system A there are a lot of voids. You can compare system A to something like thermocol or styrofoam, right? You know that styrofoam has a lot of air inside it, but you know very well that styrofoam also has excellent insulating properties. Why? Because this air that is present inside the styrofoam is not connected. There is no connection between the air voids that is inside the system A. Now system B on the other hand has some porosity, but you can see that it's all interlinked, it's all connected. That means while system B has overall a lower porosity than system A, it may still end up being more permeable because all the pores are connected. Okay, so permeability deals with connectivity of the pores, whereas porosity simply means the presence of pores of different types. Okay, so you have a structure of concrete that is highly heterogeneous, it's got pores and voids, and many of these pores are actually connected. So you form a path for the aggressive species from the environment such as moisture, sulfate, chlorides, carbon dioxide, oxygen, alkalis, all these can come in from the external environment through the interconnected pore network and deteriorate the concrete. How does deterioration happen? Of course, that is a topic of another lecture on durability itself, but I just wanted to cover some basics before we can move on to the actual testing for durability, because this basic level of information is necessary to understand what are the different ways in which you can estimate the durability of concrete. Now, this table puts in perspective what are the different types of mechanisms by which these fluids, I talked about chlorides, water, etc. What are the different mechanisms by which these fluids can actually penetrate or come inside the concrete? Now, there are several different mechanisms and they mean very many different things. So, I have given here the mechanism, the definition of the mechanism, and some test methods that actually capture these mechanisms for you to estimate the durability. Okay, first of all, you have sorption. I will discuss these in more detail, which is basically capillary action, and you have a test method called sorptivity for this purpose. Then you have permeation, which basically means flow under pressure, and you have several different permeability or permeation measurements, including air or oxygen permeability, or water permeability or water penetration measurements that can be done for estimating the permeation properties of the concrete. Then you have diffusion. Diffusion happens when there is flow under concentration gradient. That means the concentration of a species is greater outside than inside of the concrete, so the species tends to move into the concrete by diffusion. Okay, and diffusion has several different ways in which you can actually measure diffusion. You can measure it using bulk diffusion tests, using indirect tests like rapid chloride permeability, accelerated chloride migration, accelerated carbonation, and so on and so forth. Migration or conduction basically is an experiment where you are measuring the movement of ions due to an applied electric field. As I said, again I will discuss these in more detail. This is just to give you a brief snapshot of what are the different mechanisms and how we can actually use them in different test methods. Okay, wick action, you know very well that when something is dry it can actually absorb at a greater rate. So transport of ions or water from a face in contact with water to a drying surface, that is called wick action. Okay, you have absorption, which is a bulk intake of water. You then have adsorption, which is basically the sticking of water onto the surface of solids, which could be physical or chemical. And then you have convection, basically, which means flow that happens due to temperature difference. If there is temperature difference between two objects, there will be a flow from the objects based on the difference in temperature, okay, between the objects based on the difference in temperature. So let us look at how these tests can now be designed to measure some appropriate properties of concrete. Now, if you really look at something which is common to all these systems, you will realize that all durability problems require the presence of water. Without water, concrete will not have a durability problem. In terms of durability, the component that causes the maximum damage is the presence of water. So, if you have water available in the system, or if water comes in from the outside, that is when durability problems actually occur, alright. So, let us move on now to try and understand the different durability test methods and the type of parameters that we can actually measure. So, broadly speaking, you can define durability tests into methods that first of all address chloride penetration. Why is this important? Because we are trying to deal with the subject of chloride induced corrosion, okay. And then you have test methods that assess the gas permeability. Why are we interested in gas? Because sometimes we are getting carbonation, that means attack of concrete by carbon dioxide that penetrates from the external environment. Now this carbon dioxide penetration happens because of several different factors, and we need to understand what these factors are and how they can be measured in terms of the property of the concrete. Then you have test methods to assess water permeability. I already discussed that the most important characteristic of concrete that causes durability problems is basically the water. If you have more water, there is more chance of durability issues. So you have to assess how easy it is for water to enter the system, okay. So there are different test methods for that, and finally there is also a very common test method called concrete resistivity method, which I will discuss later as a very useful tool, not just for laboratory but also for the field, okay. So there are several different test methods here for durability of concrete, and each of these is measuring one parameter or the other. Now the question that comes to your mind is, in the field when I am prescribing concrete for a particular application, what test should I choose and what sort of parameter should I need to measure to understand how this concrete is going to work in the field. For that you need to have a clear idea about the environment in which you put in the concrete. For example, in the case of a marine environment, for a concrete structure that is standing inside seawater, definitely you will not be interested in understanding what the gas permeability is. You will be addressing more the issues of chloride penetration, you will be addressing the issue of water penetration, okay. So depending upon the kind of environment, you will have to then choose the type of test methods that you need to perform on your concrete specimens and assess the durability appropriately. So you can't do one test and expect it to solve all problems. Depending upon the type of environment, you need to tailor make or choose the appropriate test that addresses your particular problem, okay. So now let us try and move on and understand what are these different transport mechanisms and what are the test methods that can be used to study these transport mechanisms. I will begin with diffusion because it is a very common phenomenon. Diffusion happens whenever there is a difference in concentration of one species outside the concrete as opposed to inside the concrete. Consider for example chlorides from seawater. You know that seawater has a lot of chloride in it. Concrete, if you have chosen your materials correctly, has very little chloride inside. So what will happen now? There will be an inward movement of the chloride ions from the seawater to the concrete. And what is this inward movement going to do? It is going to increase the chloride concentration of your concrete, okay. So flow happens here of the ionic species because of concentration gradient, and that is depicted very clearly in the schematic that you have here. In the beginning you have this kind of a system in which outside the concrete you have a lot of chloride and inside you have very little or almost zero chloride. With time what is going to happen is the concrete chlorides from outside are going to start penetrating the concrete and start increasing the chloride concentration of the concrete itself, okay. Now this need not be restricted to gases, chlorides, it could also mean gases. For example, carbon dioxide can also diffuse into the concrete. The only problem with carbon dioxide is while chloride diffusion can happen in saturated conditions, carbon dioxide needs only partially saturated conditions for diffusion. So carbon dioxide cannot diffuse if the system is totally wet or totally saturated. That is the difference between chloride and carbon dioxide diffusion. Ionic diffusion happens through saturated and partly saturated concrete like chloride concrete. Molecular diffusion can happen if the pores are relatively large and the molecules can actually move in through the porous system without undergoing much hindrance or blockage, okay. So gaseous diffusion is essentially through unsaturated or partially saturated concrete. Ionic diffusion happens through saturated concrete, mostly even though I say partially saturated, mostly completely saturated concrete, and then molecular diffusion happens if the pores are relatively large, okay. So now what are the different laws that govern diffusion? First of all you have something called first law of diffusion. Now assuming that you have a semi-permeable membrane, you know very well about the reverse osmosis process, right, and what happens in reverse osmosis? You have a semi-permeable membrane and what you are doing is removing the pollutants through that membrane, and this is removed of course by applying of electrical potential, but essentially the species that are polluting the water are coming out because of diffusion. and this diffusion happens from the higher concentration to the lower concentration. Now the membrane that you use does not change its properties with time, okay. Of course the efficiency of the system will go down with time, but for the most part we can consider that the membrane is a fairly uniform and time invariant material. So the properties of this membrane do not undergo a change with time. That means that I can apply my first law of diffusion called steady state law of diffusion. Here diffusion flux is said to be proportional to the concentration gradient normal to the section at the same instant. In other words, the flux J can be represented as minus D multiplied by the concentration gradient dou C by dou X, that is the concentration gradient. So just in the schematic, if you see the concentration outside is C1, inside is C2, then there will be a flow from C1 to C2, okay, and you take the slope of that, that is basically dou C by dou X. That is related to the flow through this constant called diffusion coefficient D, okay. Now I told you very importantly in this case that you have established a steady state. That means there will always be the same difference in the concentration. C1 will be here and C2 will be here, okay. That will always be the same difference in concentration on the outside and inside. The properties of the interior concrete is not changing with time, alright. So that is what we are talking about in terms of steady state. So this is true for gaseous diffusion. For example, if carbon dioxide is diffusing, or through diffusion through thin layers like the membrane that we talked about, this kind of a test method can be suitable for membranes. What about concrete? What about concrete? Now concrete, you know, is a material that has cement, water and aggregates. The water reacts with the cement to create your hydrated cement paste. We all know very well that as long as water is available, the cement will continue to get hydrated, and if cement continues to get hydrated, you will continue to form a different structure. For example, when you test concrete at 7 days, it is going to be different from concrete that is tested at 28 days. Why? Because during this time you provided more chance for reactions to happen and structure to develop further, okay. So because of that, such a system which talks about steady state flux of the ionic material from one end to the other will not be applicable to something like concrete. So what should we do for that? For example, if you are talking about chloride diffusion in concrete, you simply cannot adopt this approach because your system, the concrete system, is constantly changing. In other words, if you really look at it, this diffusion coefficient D is not a constant in the case of a concrete, it is continuously varying. So for that, we need to move to something called non-steady state equation, that is called the Fick's second law of diffusion. Now as per this, the change in chloride content per unit time is equal to the change of flux per unit length. Now not change of concentration per unit length, but change of flux per unit length, okay. So if you look at the same system here, your concentration on one side is C1 and the concentration on the other side is C2. If you change your time a little bit, what is going to happen? The concentration outside remains C1 because, for example, seawater will have a constant concentration all the time. What is inside the concrete would now change, okay. There will be C2 will have changed now to a different level. Why? Because the concrete during this time has evolved, has hydrated more and more because of greater age that has passed on. Concrete is hydrated more and more, because of which it has formed a more denser structure. So you will have lesser of chlorides that actually get in with more time, okay. Alternatively, if you have concrete that is deteriorating with time, there is cracking happening in the concrete. So you can then imagine that the diffusion will lead to a higher concentration inside when the time increases. So again, you can think about it both ways. So in both these cases, the steady state diffusion law will not hold. So you will have to move to the Fick's second law of diffusion, according to which the concentration change over time, the change in chloride content, I have just chosen the example of chlorides, change in chloride content over time is proportional to the change of flux per unit length. Please remember, flux is defined as D into dou C by dou X. So what change of flux means? Dou by dou X of J. So dou by dou X of minus D dou C by dou X, that is minus the second derivative of the concentration with respect to the length or thickness of the concrete, okay. So in other words, the first derivative of the concentration with respect to time is equal to the diffusion coefficient multiplied by the second derivative of the concentration with respect to thickness. Okay, that is a very simple way of expressing the non-steady state diffusion. Now the problem with this once again is that your diffusion coefficient D is assumed to be constant in this equation. Truly speaking, for concrete that is not the case. Why? If your cement, for example, has some components like fly ash or slag, these keep reacting more and more with time. So what will happen as time progresses, the diffusion coefficient or the ability to resist the flow of ions and water through the concrete will keep changing, will keep increasing. You will get more and more ability to resist the flow of water and ionic species. So diffusion coefficient also cannot be treated as a constant, but has to be treated with respect to the age at which you are measuring it. Okay. So diffusion is a phenomenon that affects concrete durability. It is a transport mechanism that affects concrete durability and has to be studied to really understand and get a grasp of what is concrete durability. Okay. So now how do we measure this diffusion coefficient? Now steady state measurements are easy. For example, if you have a system in which the membrane is not changing with time, all you need to do is after a certain period of time you simply measure the change in concentration on the other side. So on the upstream side you have a concentration, on the downstream side you have a different concentration. You know that at that concentration you get a certain flux or flow of the water. Okay, like for example when you do the constant head permeability test, right, you must have all done the constant head permeability test for your sand. Okay, what do you do there? You maintain a constant head over the sand bed, and what you get is a steady increase in the volume of water that flows out. So that is basically a flux, and that is related there to the particle sizes and the permeability of the sand bed. Same thing here in a one dimensional or a steady state diffusion, what you are actually seeing is that the flux which you can measure as the flow of ions per unit time, and that is related to your change of the concentration. So you can actually measure your diffusion coefficient quite simply in this case. In the unsteady state or non-steady state, you will have to go in for some indirect way of measuring and then converting this equation. Okay, just come back to that equation here. So you have the change in concentration over the thickness, the second derivative of that, and change in concentration over time. Okay, so what you need to do is solve this equation now to get your diffusion coefficient. And how is that equation solved? What you need to do is apply something called the error function to solve this equation. I will show you the example here. Okay, so you will have to do this test first of all by chloride ponding or immersion. So the test involves taking your concrete cylinders and coating the perimeter, putting it inside a bucket full of chloride solution and allowing the chlorides only to come in from the surface of the concrete. That is why you are coating the perimeter of the cylinder. You are simply allowing the chlorides to penetrate from the surface. From time to time what you need to do is take samples with respect to the depth of the concrete from the surface and measure the chloride concentration. Okay, I will come to that in just a minute. So bulk diffusion test is what you commonly do. You have concrete cylinders that are placed inside a water bath, or sorry, a tank which is containing your chloride solution, and from time to time you grind some material from different depths of the concrete starting from the surface. Okay, so what will this tell you? It will tell you, and so after you make the powders, collect the powders from different depths from the surface of the concrete, you will have to then determine what the level of chloride is in each of these layers. Okay, what will that tell you? It will tell you the change in the chloride concentration with the depth, change in the chloride concentration with the depth. So you get dou C by dou X. Okay, so now using the error function you can now have the study that equation and solve it to get what is called the diffusion coefficient. Okay, so again the bulk diffusion test is covered under this ASTM standard, ASTM C1556. The method basically looks at natural diffusion under a very high concentration gradient. Generally the specimens up to 28 days are cured in ideal conditions. Generally we even cure them in saturated lime water, and then we immerse the specimens in 3% sodium chloride solution for 35 days. So for example, you want to test the diffusion coefficient at 28 days. After 28 days the concrete is actually stored in ideal conditions, then it is removed and then it is stored inside sodium chloride, 3% sodium chloride solution for 35 days. At the end of 35 days you remove your sample and you take the you collect powder specimens from different depths of the concrete, and then you are basically chloride profiling is being done. That means you are determining the chloride concentrations across the depth of the concrete, and then you solve the equation to get your diffusion coefficient. Okay. Now, the advantages of doing this kind of a test is that it is simulating something which happens naturally. For example, if you have a concrete column standing in seawater, you have the seawater which is going to penetrate the concrete from one end, okay, and then the penetration obviously will lead to more chloride close to the surface, and as you go inwards from the surface, the chloride concentration will reduce, right. So, if you take a powder sample from different depths, you will be able to estimate the chloride composition or chloride concentration in different depths and relate that to the diffusion coefficient. Now, this does not involve any electrical potential application, so you are not getting any other mechanism which is inhibiting your determination of diffusion coefficient. The problem is this is a slow test. So, I told you that it takes 35 days for this diffusion to happen and for you to measure the diffusion coefficient, and during collection of your powder samples, during collection of the powder samples from the concrete, you may lose some of this powder. So, what do you do then? You have lost a lot of representative sample, and sometimes when you are actually crushing or extracting the powder, if you have a lot of aggregate, it is very difficult to actually extract the powder because aggregates are highly resistant to drilling. Cement paste is quite soft and can be drilled, but aggregates are very resistant to drilling. So, getting good samples for chloride profiling is very difficult, okay. Nevertheless, people use this all the time, and you can use this for a natural structure also. For example, if you have a structure in seawater which has been servicing for 20 years and you want to understand whether the chlorides have reached the level of the reinforcing steel to cause corrosion or not, then all you need to do is collect powder samples from different depths, analyze the chloride profile and determine the diffusion coefficient and predict whether the chlorides are going to be building up on the surface of the steel for a long period of time or not. So, here the diffusion coefficient is then used to determine whether the resistance to chloride penetration is low or high. So, this is the classification given by researchers, okay. So, if you look at diffusion coefficient, if you have greater than 15 times 10 to the power minus 12, okay. So, the units of diffusion coefficient here are 10 to the power minus 12 meter per second. If it is greater than 15, it is a low resistance to chloride penetration. If it is 10 to 15, it is moderate, 5 to 10 is high, 2.5 to 5 is very high, and less than 2.5 you have extremely high resistance to chloride penetration. I will just give you an example. If you use a silica fume concrete of grade 60 megapascals or above, or if you use fly ash and silica fume in combination for a grade of 60 megapascals and above, you will easily get this 2.5 into 10 power minus 12 extremely high resistance to chloride penetration. If you use ordinary Portland cement concrete OPC, even if you go for a 60 megapascal grade, you will probably be only in the moderate to high range. You will not reach this extremely high resistance to chloride penetration, okay. So, very high chloride penetrations can be actually achieved only with the use of supplementary cementing materials like silica fume, fly ash, slag, calcined clay and so on. Now, diffusion can also happen for gases. I talked about carbon dioxide earlier. Water vapor can also diffuse, but that happens over a very low range of relative humidities, okay, less than 45% relative humidity. And the driving force is in this case not the concentration gradient, because you know that water vapor thrives on differences in humidity and not in differences in concentration. Okay, concentration in the case of a gas is basically the partial pressure. In the case of water vapor, partial pressure is the same as relative humidity, okay. So, humidity difference is the driving force. Now, molecular diffusion happens of water vapor, and this is governed by laws similar to permeability law, which we will talk about a little bit later when we look at Darcy's equation for water penetration, okay. So, water vapor diffusion can also happen in the system, but that we are not concerned with normal concrete. We are mainly concerned with chloride induced corrosion. So, we talked a little bit about chloride profiling and how that can help you measure a very important durability parameter called diffusion coefficient, okay. Now, before we move on to the next phenomenon of penetration, let us stop here and clarify any doubts you may have so that we can move on to the next type of transport mechanism. Please remember, what we are trying to discuss is the transport mechanism, what is causing the entry of these aggressive chemicals and moisture into the concrete first of all, and how we are measuring the property of concrete that defines the resistance against the entry of these species. Okay. So, the right way to go about it is to first understand what is the durability problem, second is what are the transport mechanisms causing these durability problems, and third is what is the durability parameter that addresses that specific transport mechanism. Okay. So, we will now move on to permeation, but before that let us discuss some questions that you may have either from the content that we already discussed here or the content that we had covered in the previous two segments also. Alright, so no problem, you can ask your questions now. Let us discuss a little bit about durability in your questions, and we can also discuss if you want to understand this phenomenon of chloride diffusion better and how to actually measure this bulk diffusion coefficient. Okay, there is a question which talks about how silica fume can be used in the concrete to reduce the chloride effects. Okay, so now please, I do not know if you have studied a lot about silica fume. Silica fume is a very fine mineral additive that is added to the concrete. Now the silica fume has particle sizes that are much smaller than that of cement. When you use silica fume as a replacement of cement, it leads to an improved packing of the concrete. That means the concrete becomes more impermeable or dense. So since permeability is reduced, the amount of interconnected porosity that is there for diffusion to happen. Please remember the diffusion also needs interconnected pores to happen. If there are no interconnected pores, if you have a solid wall, obviously your chlorides cannot get in because your diffusion coefficient will be very high. When silica fume is used as a cement replacement, that is what really happens. You are essentially making a structure which has very little interconnectivity in the voids, and because of that you get this extremely high resistance to chloride penetration. There is another question about what is the percentage of hydration that happens at 28 days. Now question is good, but the answer is difficult because it relates to the type of cement that you are using. For example, if I am using a cement that is my plain ordinary Portland cement, I can assume that by 28 days I am easily getting close to 90% of the potential hydration, close to 90%. But if I am using a Portland pozzolan cement, for example a cement there where fly ash is used as a substitute for ordinary Portland cement, in that case my hydration at 28 days will only be about 70 to 75%. I may not be close to 90% that I get with OPC. If I use very higher amount of fly ashes, for example 40-50% fly ash as a replacement of cement, then by 28 days I may even get only about 50% of the hydration. Okay, so it all depends on the type of cement. So you have to actually study that, and there are ways to actually determine that also. Okay, there is one question that relates to the last lecture. The question is, what is the relevance of secant modulus of concrete? Okay, now I will just since I do not have the presentation open, maybe I will just do this on the board just to explain to you what is secant modulus. So if you remember, we talked about the fact that the stress strain diagram of concrete is linear to begin with, but then it soon becomes non-linear, and I said that non-linearity is generally introduced because of the interfacial transition zone in the concrete. So you have some linearity to begin with, but soon your concrete starts behaving non-linearly. So you have a situation where you can't really truly define a yield point of the concrete. So in other words, if I take the slope of stress versus strain at any given point, the slope keeps changing as my load changes. That is because of the non-linearity. In the case of steel, if you remember your steel stress strain diagram, you have a nice linear portion, you have yielding, and then you have your strain hardening. So in that case you have a well defined yield point in the case of steel. In concrete it is not the case. In concrete what we have to do is work with this non-linearity. Now we discuss a little bit as to how cracking happens inside concrete. I told you that up to about 30 to 40% of the load, the cracks are only in the interfacial transition zone. So up to 30 to 40%, if I remove my loading, I can estimate my concrete can actually spring back to its original position. Okay, so that means if I have a load of about, so sigma 1 So if this is your sigma ultimate, if sigma 1 is about 30 to 40% of sigma ultimate, that means 30 to 40% of the ultimate strength, then what I need to do for determining the modulus of elasticity is that, oh sorry here, so I draw a line, a straight line from the origin to the sigma 1 and determine the slope of that straight line, and that is my secant modulus, okay, from the origin to the point, that is, maybe I will draw it with a different color so that it is a lot clearer. So I draw a secant or a point from the origin to the point which is about 30 to 40% on the curve, okay, 30 to 40% of the ultimate stress. So that slope is called the secant modulus. So I said before that because of the non-linearity, you can't truly define a single modulus of elasticity for the concrete. What is accepted in most codes as the modulus is the secant modulus. Okay, again the question is a continuation of the previous one. So the question is, in design, which modulus will be taken? So as I told you earlier, all codes agree primarily on determination of modulus by the secant modulus method, and this is the kind of modulus that will be considered for design purposes also. But just to refresh your memory, in the past I talked to you about the fact that many labs or many design organizations do not even do a test for the modulus of elasticity. Primarily the test, primarily they use these relationships between strength and modulus to predict the modulus of elasticity from the compressive strength. Now I know that is not a correct approach to do it. Wherever possible, one has to test the modulus of elasticity separately, because especially for the modern concretes where we are dealing with very high strength levels, you need to actually determine modulus, because the relationship between strength and modulus of elasticity does not really apply quite nicely to modern concretes, okay. So wherever possible, we have to determine modulus separately, and that modulus which will be used for design purposes is your secant modulus of the concrete. Yeah, again, so the question, there is a continuation of that. 5000 times square root of FCK, is that secant modulus? That is the question raised once again by the same person, and yes indeed, that relationship that is prescribed in your IS code, that modulus equal to 5000 square root of FCK, is based on some data fitting through experimental data where modulus has been measured by the secant modulus method and strength has been measured by a normal measurement as per IS 516, and that data has been fitted into this equation, that is E equal to 5000 square root of FCK. So that is basically secant modulus. Okay, so we will move on now to the next segment, and you can always revisit what we have discussed before to come back and get your questions answered on what we had discussed earlier, okay. So let us continue now with the different mechanisms of transport that lead to the penetration of aggressive chemicals and water into the concrete, okay. So we discussed about diffusion that happens because of difference in concentration of ionic species inside and outside of the concrete. Now what if there is only a pressure? For example, you have a concrete block that is kept inside a water tank, and you have the pressure of the water because of the height of the water on top of the concrete. So what is this going to do? That pressure is now going to drive the water into the concrete. So that is called permeation. Permeation is basically saturated liquid transfer controlled by a pressure gradient across the concrete. Because of pressure gradient, this flow of the water is happening across the concrete, and because of water moving, obviously the other things along with the water can also move, like chlorides, sulfates, or whatever the aggressive species may be which are dissolved in the water. When water moves by permeation, all the other species also will tend to move into the concrete. For example, in the case of a swimming pool where you have a large height of water, the water permeation will be one of the major factors through which the water is actually able to penetrate into the concrete. And you know that concrete, especially when it is subjected to tension, has a lot of cracking, and if cracks are present, obviously your chances of permeation happening are a lot more, okay. So needless to say, if you design a concrete that is extremely good in terms of its permeability, it's still, if it's free from cracking only, it's going to be durable. If there's crack present in between impermeable concrete, it's not really going to be of any help. So permeation will be greatly enhanced if there is cracking present in the system. So these are connected porosity through which permeation is happening, and if there is cracking present, obviously that is going to increase the level of flow that happens of water through the concrete. So you all know this very well, that permeability is governed by, under a constant pressure head, the permeability is governed essentially by Darcy's law. Darcy's law at steady state, please remember this is again steady state, we are talking about the state at which you get a constant flow of water at the other end, that is called a steady state, just like what we had in your constant head permeability measurement in sand. Okay. So here Darcy's law at steady state says that Q, which is the flow, is equal to K, which is the coefficient of permeability, multiplied by area A multiplied by the pressure gradient, that means the difference in pressure divided by the length over which the travel is happening. Okay. So Q equal to Ka delta P by L. So that is basically your Darcy's law, and K is the Darcy's coefficient of permeability. Okay. Now this Darcy's coefficient of permeability K can also be related to something that is a material characteristic, does not matter how the test is done. Okay. So in that case, the material permeability, which is called intrinsic permeability D, can be related to Darcy's coefficient K as D equal to mu times K divided by rho times G. Of course, rho is the density of the liquid, G is the acceleration due to gravity, K is your permeability coefficient, and mu is the viscosity of the fluid that is actually penetrating. Okay. That is basically your material property, the intrinsic permeability. The permeability coefficient that you measure through the experiment is an experimentally determined property, but if you want to convert that into a material parameter, that is called intrinsic permeability. And of course, you also have another law, if you have a gaseous system, gas penetration that is happening inside, that is happening because of pressure difference, okay, and that basically can be related to the Hagen-Poiseuille equation. Okay. Hagen-Poiseuille equation again looks at the incremental volume penetrating over an incremental period of time, the same sort of an equation as you have in this case of the Darcy's coefficient here. So this is an experiment with which many of us are quite familiar with, at least in the case of sand. When we try to measure the permeability of sand, we do the water permeability test. In terms of concrete also, this is a true indicator of how permeable concrete is to water, how easily it allows water to enter. So it measures basically the steady state permeability coefficient for water flow under a constant pressure head. In other words, I have my concrete specimen, I maintain a certain pressure head of water above that specimen and measure the amount of concrete of water that flows out of the concrete, and at the stage when the flow of water becomes constant, that means I get so many milliliters or cubic centimeters per minute or per hour constant flow, then I can determine by Darcy's law the permeability coefficient of the concrete. But can you ever imagine how long that would take? So you have a water pressure on one side, you have the concrete specimen, and now you are waiting for this water to trickle out at a constant rate, mind you. That is very important, because only when it is constant at the other end can you call it a steady state. And for steady state to be achieved in concrete, it may take you anywhere between 10, 15, 20 days depending upon the type of concrete. Now you want to test the property of a concrete at 28 days. If it takes you further 20 days to get steady state itself, then what relevance would that test have? No, nothing. So what happens in the case of concrete is water permeability test, which relates to flow of water through a concrete specimen to the other side, that is hardly ever done these days. If you look at IS Indian standards 3085, IS 3085, that is basically a test which is similar to that. But nobody uses that test today because it is simply impossible to measure this steady state flow in a reasonably short period of time. It takes very long for the steady state to be obtained. Okay. So we have to move towards other methods of measurement of this water penetration, and that can be obtained by actually taking your specimen and after a certain amount of time has passed, splitting the specimen and finding out how deep has water penetrated. That is a more acceptable test nowadays because that is done within about 3 days from the time at which you start the test. So this is the two ways in which you can do it. So this is your concrete specimen, which is properly sealed on the sides, mind you. It is very important to seal the specimen on the sides. Why? Because when you are causing this flow to happen, it should happen only through the concrete, not around the concrete. So all the periphery has to be sealed very effectively. That is another difficulty of this test. It is impossible to get that sealed properly. Okay. So you have concrete water flowing through the concrete and is collected on the other side, and you are measuring basically the flow rate of the water in steady state. That means flow rate is going to be constant at steady state. Okay. In the other test, what you do is after a certain amount of time has elapsed after application of your pressure head, you simply split open your specimen and find out the depth of water that is penetrated. That is a much easier test. It typically is running for only 3 days. Okay, so you apply the pressure, after 3 days split open the sample and determine the depth of penetration. That is called the water penetration test. It is different from the water permeability test. So water permeability or water penetration test is done as per a German standard, which is DIN 1048 part 5. It is a German standard which is now also a European standard or EN standard. Okay. So this is the equipment for it. Okay, this is the equipment. So here you have cells that can have 3 specimens, 3 cube specimens or 3 cylinder specimens can be tested at a time. You maintain your pressure of water over the specimens by using the water column that is provided on top, okay, and these are gauges which help you maintain the correct pressure of water on top. You typically maintain a pressure of 0.5 Newton per millimeter square, 0.5 Newton per millimeter square. You apply that pressure for a period of 3 days. Okay, you apply the pressure for a period of 3 days, and then at the end of 3 days you remove the sample or remove your specimen and split the specimen into 2 like what is shown here. Okay, so this is a specimen that has been split into 2 and you can clearly see that up to a certain depth water has actually penetrated. You can clearly see the depth of penetration of water in that specimen. So that depth of penetration obviously relates to how easy it is for water to enter the concrete or how difficult it is for the water to enter the concrete. Okay, so you are getting a measure of the resistance to penetration of water or even resistance to permeability of water. Truly speaking, it is penetration, but sometimes we can also call it as permeability. Okay, so this is a very easy test to conduct. The equipment is not very sophisticated, does not require very major systems to be established in the lab, can be done quite easily. Depth of water penetration is measured and it is directly related to actual performance, because even in regular site conditions that is what is happening, right. You have a pressure of water which makes the water penetrate the concrete, and we are mainly interested to see whether the penetration is equal to or greater than the cover of the concrete, because again the cover is protecting the reinforcing steel from corroding. So if it takes long time for the water penetration to be equal to the cover of the concrete, that means your structure is fairly durable. Okay. The problem with this test obviously is that you are splitting open your specimen, so it is a destructive test. You are breaking your specimen, and this pressure gauge that is on top here, it needs an air compressor to maintain the pressure constant. Okay, so you do require some additional components to ensure that you are able to get this. Okay, but even in the case of water permeability test, which measures the IS test method that I talked about earlier, which measures the flow rate on the other side, even there you need some sort of a compressor to ensure that you are maintaining a water pressure on top of the water head, on top of the specimen. Okay, so water penetration or water permeability test as per the German standard DIN is a very common test, and today if you look at many of the specifications for concretes that are prescribed for metro construction, for instance, or even bridge construction, a lot of the consultants are prescribing the water penetration test to be done for concrete that is supplied to the site. That means that all the concrete that is supplied to the site must not only meet strength requirements, it must also meet water penetration test requirements. There is also another non-destructive test method called German water permeability test. Now this is actually a non-destructive test and it is a very proprietary test. You see this fixture here, you have to clamp it on top of your concrete surface and you apply a pressure difference to the water that you pour in, and then at that pressure difference you need to actually, you are not applying a pressure difference when you are actually pressurizing the water to penetrate the concrete. There will be a difference in the gauges that you are basically trying to read in the instrument itself. So pressure is kept constant using a micrometer gauge with an attached pin that reaches into the chamber. So as the water keeps penetrating, the position of the pin changes, which can then be traced back to the permeability coefficient. Okay. So this is non-destructive, it can be used for both laboratory and field measurements, and then problems are the pressure may be not sufficiently large for impermeable concrete. So if the concrete is of a very high quality, you will not get anything from this test at all. And if you have surface porosity which is not uniformly distributed, you may actually get some leakages in this instrument which is not easy to resolve. Nevertheless, there are some criteria that you can use to determine the quality of your concrete. For example, the coefficient of water permeability as per some classification criteria, if it is less than 10 power minus 12, your concrete quality is good. If it is greater than 10 to the power minus 10, the concrete quality is poor. Okay, so different estimates can be given for the quality of your concrete based upon the performance in this test. Now, a similar concept of this water permeability by the German instrument is applied for the determination of gas permeability. Now, once again, you are measuring under a pressure head what is the penetration of your fluid into the solid. Okay, we talked about water first, in this case we are talking about gas. Okay, so what we are doing is we have this vacuum cell which is placed on the surface. You are evacuating the region close to the surface. Okay, what will happen when you evacuate or create vacuum there? Air from the other parts of the concrete will try to now enter this chamber, and the more permeable the concrete, the faster this air will enter that chamber. Okay, so basically you are measuring the permeability by creating vacuum and then measuring the change in pressure that happens when air gets driven into the chamber. Okay, so that is called gas penetration measurement, and it is measured essentially by this method called torrent air permeability. Again, this instrument is shown here, it's in a box, and you can use this instrument in laboratory specimens as well as on site. You basically fix your chamber, that is the chamber that is shown here, you affix the chamber onto your concrete and apply vacuum. So when you apply vacuum, the regions close to the surface of the concrete are totally devoid of air. So what happens now? There is air from outside which now starts getting into the concrete and fills up this and changes the pressure in your chamber. It changes the pressure in your chamber, and that is what you are trying to measure. It is a simple test, it is non-destructive, and as I said before, it is suitable even for the site. Only problem is if your concrete is sensitive, if your concrete is moist, or if there is moisture present inside the concrete, you will not be able to get a suitably good reading from this. And again, if your surface condition of the specimen is not very good, for example, if you have differences, if you have some spots which are porous and so on, you will get a lot of problems in trying to get the vacuum established on the surface. Nevertheless, you can use this test to once again give qualitative classifications for your concrete. So the test measures something called the torrent air permeability coefficient into 10 to the power minus 16 square meter. So this is the kind of criterion, a logarithmic scale that is established to relate to the concrete quality. Okay, so you get something, some number which tells you whether your concrete is good or bad, and that is a very valid and very required sort of an estimate of concrete structures that are on the field. So this test has been standardized in the Swiss standards and may soon also become a European standard. There is another European test method, in which case what you do is you have your, this is South African test method, in which you are having a pressure cell which is filled up by a gas. You have your concrete sample. What is going to happen is with time that gas is going to flow out of the concrete and the pressure in the cell is going to get reduced. So by measuring the decay in pressure in the cell, you can relate it to the gas permeability of the concrete, and that is what is done in this test, which we otherwise called the OPI test, Oxygen Permeability Index test. I will show you once again how this is done. So this is your pressure cell here, and that gauge that you see there is the pressure gauge. So you fill up the cell with a certain pressure, about 120 pascals. Okay, you have your concrete specimen sitting on top here, that is encased in a steel collar to ensure that it is compressed properly between the cell. So that is your concrete specimen here. You allow the oxygen that you fill up in the cell to pass through this concrete specimen. Over a period of 6 hours, you keep measuring on a timely basis what is the pressure inside the cell. So as the oxygen keeps penetrating through the concrete, the pressure inside the cell will keep reducing, and then you can apply this Hagen-Poiseuille equation to actually get your coefficient of permeability to oxygen. Okay, so you get coefficient of permeability through oxygen, and you can relate that to the permeability index by taking a negative log of the coefficient of permeability. For example, we know that permeability coefficients are of the order of 10 to the power minus 5, 10 to the power minus 10 and so on. If you take negative log of that, you get actually an index number which is positive, okay. The lower the permeability, the greater the index. For example, when you have 10 to the power minus 10 and 10 to the power minus 12, when you take the logarithm, 12 obviously will be greater than 10, but the permeability in terms of the 10 to the power minus 10 and 10 to the power minus 12 is lower for 10 to the power minus 12, okay. So the index is greater when the permeability is lower. So again, this is a good test to be done within a reasonably short period of time. Only thing is, here you need to obtain the specimens carefully. So how do you do? In the case of your water penetration test, you just had the cube specimens, 150 mm cube specimens. In the case of oxygen permeability index test, what you will have to do is you take a core through your concrete. Okay, maybe I'll just come back to that and show you the specimen preparation separately. But what you do is you take a core through the concrete, you make slices 30 millimeters thick and use those slices for these tests, okay. So that's the slices 30 millimeters thick are used for the oxygen permeability index test. The detailed procedure is given in the manual, and I have also attached a copy of that inside the lecture notes that have been uploaded on your course pack. The problem is it is sensitive to macro voids and cracks. If your concrete has macro voids and cracks, then the decay in pressure will be very rapid, and then it is sensitive to the edges of the specimen. So if your edges are not very good, if you have like blunt edges instead of sharp edges, there will be leakage of oxygen, and then it will be very difficult to conduct this test. So as in the other cases, you can again use an estimate of the oxygen permeability index to come up with a qualitative classification of your concrete. So greater than 10 is very good, less than 9 is very poor, okay. So in other words, we are talking about greater than 10 means my permeability index is less than 10 to the power of minus 10, okay. Less than 9 means my permeability index is greater than 10 to the power of minus 9, okay. So that means I am getting a very poor quality of your concrete. There is one more gas permeability test again, which measures the gas flow through the sample, and here you have constant pressure maintained in the cell. Please remember, in the oxygen permeability test, the pressure in the cell continuously decreased, but here in this new test called SEM-Bureau test, you can keep the same pressure and measure the flow rate of the oxygen through your sample. So that is like a constant head permeameter test. The South African method was a falling head permeameter test, so that is the only difference. Now any gas penetration test that we do has to be related to some natural phenomena that happen, and I told you that the main natural phenomena that happens is actually the carbonation or penetration of carbon dioxide into the concrete, and that can be actually done in a faster way using accelerated carbonation test. In reality, concrete structures are exposed to the environment, and the atmospheric content of carbon dioxide is about 0.03 to 0.04%. At that rate, it will take years for your specimen to get carbonated. So you can create similar conditions in the laboratory by choosing to work with these chambers. You see this chamber here on the right, that is a chamber in which I can control the temperature, the relative humidity and the carbon dioxide concentration. So what we typically do is we have a higher concentration of carbon dioxide used, and that carbon dioxide penetrates the concrete specimens, and then over time we keep measuring the depth to which the carbon dioxide penetrates, okay. So you subject your specimens, typically prismatic specimens, to exposure to a high carbon dioxide environment, 1%, sometimes 3%, some people have done with 50% and 100% also, but those are totally irrelevant. Even 1% for instance is 25 times higher than what you have in the atmospheric carbon dioxide, but then still it reduces the test duration by a significant amount. So within a matter of about 6 months, you can get a relatively good idea about the resistance of your concrete to carbonation. So here you place your specimens inside a chamber where you can control the carbon dioxide concentration, allow the carbon dioxide to actually penetrate the specimen, and measure the depth of the penetration of carbon dioxide by splitting open the concrete. So here this is the concrete that has been split open, and after you split open, on the fractured surface you spray phenolphthalein. Okay, you remember that phenolphthalein is an indicator which turns pink when there is alkaline conditions. and it remains colorless when the conditions are not alkaline. If you understand carbonation, carbonation is the process in which carbon dioxide enters and converts your calcium hydroxide into calcium carbonate. So that means you are converting something which is alkaline into something that is not alkaline. So essentially your carbonated areas which are depicted on the surface of this concrete here remain colorless, whether the interior areas, whereas the interior areas which are not carbonated turn pink on the application of phenolphthalein. Okay. So again that is a simple measure of how deep your carbon dioxide actually has penetrated. What is the problem with carbonation? We know that carbonation problem only happens if the carbonation depth reaches the surface of your steel, and when it reaches the surface of the steel, the pH around the steel becomes very low and the steel starts to corrode. Okay, so that is why we want carbonation to be properly understood to ensure that steel corrosion can be prevented in a carbon dioxide rich environment. Okay. Now of course when you have lot of carbonation in the accelerated test, that increased level of carbon dioxide may actually completely change the mechanism by which this carbonation happens. In real life you are only working with 0.04% in natural carbonation. Here you are working with 25, 50, 100 times stronger concentrations of carbon dioxide. So you may not always get the same chemistry of this phenomenon that you observe in real life. So that may be one of the disadvantages of the accelerated carbonation test. Okay, now we will take a brief break here, come back to some questions, and then we will take up the rest of the slides in the last section of this presentation. Okay, there were some questions that were previously loaded. One was how chlorides and sulfates affect the concrete. Now please remember, chlorides per se do not have any major disastrous effects on the concrete itself, but chlorides have a major effect on the reinforcing steel. Generally when the reinforcing steel, at the level of the reinforcing steel, when the chloride concentration reaches about 0.4% by weight of the cement, at that point you can start initiating the corrosion of the steel. So what you need to ensure is you design your structure to have a life which is sufficiently long enough, and that life is basically governed by the time it takes for the chloride to reach that concentration on the surface of the steel. So you design your concrete in such a way that the cover is large enough for that, and your concrete property, that is impermeability, is good enough to prevent further penetration of chloride. Sulfates on the other hand penetrate the concrete along with the groundwater. They interact with the cementitious materials like calcium hydroxide and CSH and lead to formation of other compounds like gypsum and ettringite. Those compounds may lead to expansion, loss of strength, because of which your concrete becomes difficult to work with and becomes unstable, unserviceable in environments which are rich in sulfates. Now there is a question as to why IS codes are not available to test the durability properties of concrete. That is a very good question. There is no reason why IS codes should not be available. Now what happens is durability tests have not yet been included in the IS standards, and what happens is, as of now, the performance parameter that people test on site is simply the compressive strength of the concrete that is supplied for construction, and that is because that is the only parameter that is specified in your IS 456. It is only when we start taking cognizance of the fact that it is not just the strength that is important, it is also the durability that is important. So far people have been believing that the stronger the concrete, the more durable it is, which is not correct. You can make even a weak concrete durable by choosing your materials appropriately. Okay. So what we are trying to say is, once you understand that concept, you will now be able to now start prescribing doing durability tests also. And once prescription for durability test comes inside IS 456, then obviously there will be a need for standardized durability test measures. If you look at European and American standards, they already have several standards for different durability test methods. So it will only be a matter of time before we revise our own codes and standards to reflect this development, and soon there will be sufficient inputs of durability also in Indian standards. There is a question on the chat which says, will you please explain us about the interfacial transition zone? Okay, once again let me just use the board for that, it will make things clearer. As we had discussed previously, concrete is a multi-phase material. So if you think about concrete, okay, you have aggregates inside concrete and fine aggregates also are there. Let us not consider fine aggregates for now because they are too small right now. Let us consider coarse aggregates. Now you know that the coarse aggregates are very stiff, or they are highly strong as opposed to the paste that is surrounding them. So let us consider the example of the paste that is surrounding the aggregate, that is your cement paste. And then you have paste that is away from the aggregate here, that is also paste. The only difference is this paste is in the zone of bonding with the aggregate, so that is paste in interfacial zone, and this is paste which is in the bulk, okay. So now what will happen is, if you look at the structure of concrete, when you mix the concrete, because of the dissimilar properties of your aggregate and paste, there is a good chance that there is insufficient packing of the paste around the aggregate. And you also know about bleeding, right? What happens in bleeding? In the case of bleeding, you have aggregate and water is trying to go up, water is trying to rise up, gets trapped under the aggregate. The water which is trying to rise up, because it is the lightest ingredient in concrete, gets trapped under the surface of the aggregate and creates a large pore there. So that is a pore, that is an aggregate again. So it creates a large pore there. In other words, you are creating a region which is around the aggregate which is weaker compared to away from the aggregate. This zone away from the aggregate where the paste is present is quite dense and impermeable. On the other hand, the zone right around the aggregate is highly porous and permeable. So that zone which is porous and permeable is called the interfacial transition zone, okay. So interfacial transition zone is a zone of bonding between paste and aggregate. It is generally more porous, more permeable, and it also has much more defects like cracks inside. Now why is that the case? Now consider the same concrete which you are going to be loading. So you know that when you have mixture of two or more faces which have different stiffnesses, when you apply the load is going to get attracted by the stiffer face. So when you start application of the load, it is the aggregate which will take up a bulk of the load. So since the aggregate is taking a bulk of the load, the zone around the aggregate, even at very small load levels like 20-30%, even at that load level, this zone will be subjected to very high stresses as opposed to the zone away from the aggregate, okay, because of which there will be more chances of cracking happening right here at the interface. So interface is porous, interface is permeable, interface can be cracked at very low load levels, because of which ITZ or interfacial transition zone, okay, interfacial transition zone that is basically called often as the weak link in concrete. That is the link through which failure happens, through which your flow of liquids and penetration of aggressive species also happens. I hope that was able to explain something about interfacial transition zone. There is one more question: in actual practice, whether permeation happens through the sides of the concrete, but in test procedure the sides are sealed. Not able to quite understand that. Now here what you are simply trying to do in the test procedure is having a unidirectional flow, okay. That is why we are sealing the sides, okay. We are having a unidirectional flow to ensure that there is flow only in one direction, okay. That is why the sides are sealed, okay. We are not truly simulating what is happening in the field, but the idea is to create this unidirectional flow. Only then we can apply the right strategies to measure the permeability coefficient or penetration of the water, okay. I am not sure what this question is. The question says, can you please say some cement examples for low chloride penetration? Okay, for types of cement that will cause lower chloride penetration. I hope that is your question. If that is the question, the answer is that the cements that are substituted with mineral admixtures like fly ash based Portland pozzolan cements, slag based Portland slag cement, those are very good against chloride penetration. Especially when you consider marine environment, you should never use just plain ordinary Portland cement in those cases. You have to use blended cements like PPC or PSC because they can bind chlorides much better and prevent the penetration of chlorides deep into the concrete. So problem happens only when the chlorides reach the surface of the steel. That is when they start causing problems of corrosion. In the case of blended cements, the chloride is not allowed very easily to get to the surface of the steel. One question relating to how pH of water affects concrete. Now, please remember concrete is a highly alkaline environment and you need water to react with the cement and produce this alkaline environment. Now, the original pH of the water has to be kept to as neutral as possible, because what happens is when you have a high alkalinity in the water, that means you have presence of some alkalinity causing species. High acidity in the water, that means you have some presence of acidic species in the concrete. They may interfere with the reactions that take place with the cement compounds. So pH of water has to be kept as neutral as possible when you mix it into the concrete. That is why if you look at any standards, there are strict limits on the pH, there are strict limits on the alkali content, there are strict limits on the sulfate content of the water, because all these have to be satisfied. In other words, if you look at most standards, water has to be potable. What does that mean? It means that water that you can store in your pot in the house and drink, okay, that is the drinkable water, is what is prescribed to be used for concrete. Of course, we have to deal increasingly with sources of water that are not drinkable, but still have to be used in concrete because there is severe water scarcity otherwise. But needless to say, water has to be used which is free from all these aggressive chemicals to begin with. Otherwise, you are in the beginning itself creating a lot of problems with the concrete. So, water has to be as neutral as possible. Okay, so we talked about water permeability and different methods of measuring water and gas permeability. Now, what we will talk about is sorption or capillary water absorption. Now, consider a case in which there is a concrete which is partially dry or almost fully dry and you put it inside a tub of water. What is going to happen now? There is going to be a capillary rise of water through the dried concrete. Why? Because concrete is dry, it is not saturated. This capillary rise will soon conduct the water from the outside into the inside. So, basically sorption or capillary water absorption deals with uptake of liquid into unsaturated or partially saturated soils, okay, partially saturated solids. This is influenced by presence of capillary pores and degree of continuity of the pores. Please remember, I talked earlier about the fact that it is not important that you have lot of pores. What is important is whether these pores are connected or not, okay. The aggregate orientation, the degree of compaction, the mix composition, all those will have an effect on the sorptivity or capillary water uptake. And this is one of the experiments that can be done very simply by creating conditions of capillary rise in concrete, okay. I will show you how this is done. First of all, what is the equation of sorption? Basically, this is a Laplace equation which relates the capillary pressure to the diameter of the porosity, right. That is your diameter of the pore, that is your capillary pressure, sigma is the surface tension and theta is the angle of wetting of the liquid, okay. That is your capillary equation, you remember this very clearly, and this equation basically relates to the capillary rise through the concrete, okay. So, now what you do, how do you measure this capillary rise? Obviously, you can't go around measuring with the scale how much water has risen into the concrete. So, you can indirectly do this by measuring it by mass. So, you measure the mass of the concrete and simply plot it against time. You can solve the Laplace equation using that and then work out your coefficient of sorption or sorptivity. What do? You take a concrete specimen, once again you seal the sides because you want the penetration to happen in a unidirectional fashion. You seal the sides, you place it in a tub of water so that the water is only touching the bottom, it is not creating any pressure. Mind you, there is no permeation happening here, there is just capillary absorption. So, this concrete sample after sufficient amount of drying and sealing of the sides is placed in a water tub, the water is just touching the bottom. So, there will be capillary uptake, and what you do is at different intervals of time you take the specimen out and measure its mass. So take it at 1 minute, at 3 minutes, 5 minutes and so on, and keep placing it back after you measure the mass. So what is going to happen is you are going to get a relationship between the mass that is absorbed by the specimen against the square root of time. When you plot it against the square root of time, you will see that the initial points in this plot form almost a straight line, and that regression line through the initial data points, which is called, the slope of that line is called the capillarity index or sorptivity of the concrete. Okay. So again, this is a typical test that is done for bricks also. Remember, for bricks what you do, you place it in a water, and that water basically gets capillary absorbed into the brick and comes out with any salts that are there in the brick, and you can actually study efflorescence with that test method. That is efflorescence test method. But then similar test method here, you are putting a concrete sample inside a tub of water. The water is now coming in by capillary sorption, and you can actually measure the rate at which that capillary sorption is happening by plotting the mass absorbed over the square root of the time that is taken, and that initially the data points will actually give you a straight line. The slope of that line is called sorptivity. The sorptivity test is very simple. Again, you use the same specimens that were earlier used for oxygen permeability. Please remember, sorptivity is done on specimens that are similar to oxygen permeability. I will show you the method of specimen preparation on the board. So you have your concrete cube. You have a 150 mm concrete cube, which we typically make for determination of compressive strength. Okay. So what you do is you take a coring machine and you drill it into this concrete cube and pull out a concrete cylinder or cylindrical core of 69 millimeters diameter, 69 millimeters diameter. Okay. And then what you do is you simply slice it into slices of 30 millimeters. You slice it into slices of 30 millimeters. Why 30? Because once again we are interested in relating this to the cover properties of the concrete. So imagine that you have a slab in the field and you want to test the durability of that slab. So you pick out a core from the slab and cut the top 30 millimeters, and that will be your sample for understanding how good your concrete in the field is. Okay. So you take 30 millimeter samples or specimens, you dry it, you dry in an oven for at 50 degrees Celsius for 7 days. Now you know that obviously the best method of drying is to put it at 110 degrees Celsius. That will drive off all the water. But the problem with drying at such high temperature is that it may start inducing cracking in your concrete. To avoid the cracking, people have suggested that we can dry for a longer period of time, that is 7 days, in a smaller temperature of 50 degrees Celsius. Okay. So you can prepare your sample that way, and after the drying is completed, you can do your oxygen permeability test first. Okay. Then use the same sample to do the sorptivity test. You can use the same sample to do the sorptivity test. Okay. So for sorptivity test, what you will do is you will coat the periphery also to ensure that the water is not rising from the sides, it is only rising from the bottom. So that is your slice of concrete. You will be coating the periphery of the concrete so that water uptake happens only from the bottom of the concrete. So water rises only by capillary action. Okay, so that is the method of specimen preparation for the oxygen permeability test and water sorptivity test. So water sorptivity test simply means that you are putting this concrete in a tray of water. Actually, instead of water you can also use saturated calcium hydroxide solution, because if you just use water there may be some ions from the concrete that may come out into the solution. So instead of that you can have calcium hydroxide solution which will prevent any leaching from happening. So even here what you are simply doing is measuring your mass absorbed, plotting against square root of time. The slope of that initial part of that plot gives you the capillarity index or sorptivity of the system. That sorptivity, again through some classification criteria suggested by researchers, can be related to the concrete quality. If you get a sorptivity of less than 6 millimeter per square root of R, it is very good. greater than 15, it's very poor. Okay. So again, you can use different measures to understand whether the concrete that you have put in the structure is of a good quality or not. So this simulates natural phenomena, especially where the concrete is going to be in contact with a liquid medium on one side. It is applicable to drilled cores. That means you can actually take cored specimens from your structure and study sorptivity on those cores also. Problem is, again, it's sensitive to macro voids and cracks. It is sensitive to microstructural properties of near surface zone of concrete. For example, if the concrete surface has been altered because of carbonation, you will obviously get a difference in sorptivity. And then because you are actually pulling out a sample from the structure and not measuring directly on the structure, it's a destructive test because you are taking the core out of the structure. Okay, but then it's a very useful test. In the site, it's very useful to determine whether you have done curing properly or not. So concrete that is cured properly will have a very low water sorptivity. Concrete that is cured improperly will have a greater water sorptivity. That means it will perform poorly in the case of the water sorptivity test. Now the simplest phenomenon that you understand is absorption. You take a dry sample, put it inside water, allow the water to completely absorb into the sample, remove the sample and measure the change in mass. That's the simplest measurement. You do it all the time to determine the water absorption capacity of your coarse and fine aggregate. You can do the same for concrete also. Only problem is, if you use normal temperatures, the water absorption may not stabilize for a long period of time. So people sometimes use boiling water instead of regular water to ensure that the water is penetrating completely deep into the concrete. Okay, so it's easy to measure, but it's difficult to penetrate all the pores of concrete because you cannot have a system in which water is penetrating everything. That's why boiling water is sometimes used. So this is covered through different techniques. One is the simplest measurement, in which you simply put it inside normal water and measure the difference in masses for a oven dry specimen and for a completely wet specimen. Or you can do it with boiling water to increase the accuracy of the data and also reduce the time that you take to actually penetrate. Or you can do it by vacuum saturation. So here what you do, you place your specimen inside water and apply vacuum. So what happens when you apply vacuum, all the air that is trapped inside the concrete porosity will simply come out and water will go into the pockets that are filled up with air. So you get a much better estimate of the porosity by vacuum saturation. And the boiling water and normal water method is covered in ASTM C642. Again, a very simple test procedure where you can work with different types of chunks of concrete directly without really having to prepare a specimen. Now another complicated phenomenon that happens sometimes is adsorption. Let's not talk about that here. Adsorption is basically attachment of liquid molecules onto the surface of the solid. So let's keep away from that because there are no real test methods that can help you understand this very clearly in a short period of time. Let's move on to another set of tests which is very commonly used for concrete durability, and this is based on migration or conduction. So why do I say migration in this case? I told you earlier, migration happens when there are ionic species that are getting driven by difference in electrical potential. Okay, so for example, you have chlorides on the outside of the concrete, right? And these chlorides are going to get into the concrete by diffusion. Now what if you apply a potential difference also? What's going to happen, because chloride ions are charged particles, they are going to move because of the potential gradient also. Okay, so not only are they moving by diffusion, they are now going to move by potential gradient also. Okay, that's called migration. Okay, so migration again is covered very effectively by the Nernst-Planck equation. So you have basically you're relating the coefficient to Faraday constant, the temperature, and the change in the concentration over unit length. Sorry, not change in change in potential over the unit length. Okay, so this is a snapshot of a concrete which has two cells here. One is a positively charged cell, one is a negatively charged cell. That means you have applied a potential difference between two electrodes. Your concrete is sitting inside in a saturated condition and you have different ions moving in different directions. I will describe the test method for which this applies in just a minute. So how do you measure migration? Migration is easily measured by applying an electric field across the concrete in a saturated medium with different sorts of ionic species. Okay, so you have one upstream cell which is the cathodic cell, and downstream cell which is the anodic cell. Okay. So how do you measure in practice? We do it most commonly using what we call as the rapid chloride permeability test. So rapid chloride permeability test has this cell here, you can see the cell here, there are 4 cells which are getting tested simultaneously. Your concrete specimen is actually a cylindrical specimen of 100 millimeter diameter and 50 millimeter thickness. Okay, please remember earlier I talked about sorptivity and oxygen permeability where you had a 69 millimeter diameter core specimen. Now here you can have a 100 millimeter diameter specimen with 50 millimeters thickness which is placed between the 2 cells. So what you do, you fill up the negative side of the cell by 3% sodium chloride solution and positive side, that is anodic side, with 0.3 molar sodium hydroxide solution. So coming back to this diagram here, so on the positive side you have sodium hydroxide, negative side you have sodium chloride. So when you have the electrical potential applied across the negative and positive sides, generally the potential is about 60 volts that is applied over a period of 6 hours. Okay. So when you apply the 60 volts potential, this is what is happening. Your hydroxyl ions which are on the anodic side are getting driven towards the electrode. Your chloride ions that are there in the cathodic side are getting driven to the positive side, right. Chloride ions are negatively charged, so they are getting driven to the other side. So to go there, what they have to do is pass through the concrete. When they are trying to pass through the concrete, obviously they will change the properties of your concrete. So here what property we are measuring is the charge that is passing through the concrete. So what will happen is when the potential difference is applied, there is a current that is passing through concrete. What we generally have is this chloride which is getting driven to the positive electrode has to now go through the concrete. The concept is that the more the chloride that penetrates, the greater is the increase in current that goes through the concrete. Okay, you get the idea? More the chloride that penetrates, the greater is the current that the concrete actually conducts. In other words, with more chloride penetration, the concrete carries more charge. Okay, so that's the principle of the rapid chloride permeability test. So current is measured every half an hour, and then for a total of 6 hours you measure the total charge. You know that charge is equal to current multiplied by time. Okay, so over a period of 6 hours you measure the total charge that passes through the concrete. And this charge once again is qualitatively related to the chloride ion penetrability of the concrete. If you pass more than 4000 coulombs of charge, that is a very high permeability concrete. 2 to 4000 is moderate, 1000 to 2000 is low, 100 to 1000 is very low, and less than 100 is negligible. So this is criteria given by the standard that is governing this test method, that is ASTM C1202. Okay, this is probably the most widely used method anywhere in the world. Why? Because it's quite relatively quick. After the specimen is ready, your test takes only 6 hours. Okay, it gives a qualitative classification of concrete that you can use to actually distinguish between different types of concrete. Please remember, this is a qualitative classification. Now greater than 4000 is called high permeability. So if you get 5000 or if you get 8000, doesn't make a difference. It is greater than 4000, both are high permeability, both have, according to this test, both have no difference, both are high permeability, that's all. So there is difficulty in interpreting quantitatively the test result. Although it gives you a number, quantification is not very easy. Okay, it is only a qualitative classification. So the current passed in this, the problem with this test is the current passed is related to all the ionic species that are moving. I showed you this diagram earlier. Look at how many ionic species there are which are continuing to move, right. Since all these ionic species will move, the charge that you are measuring or the current that is passing will depend on all the ionic species, as a result of which you are not getting truly the chloride penetrability. All you are getting is the conductivity of the concrete under an applied electrical potential. Okay, so again, if you have more conductive materials present, it will affect your test results. For example, if you have a concrete which is filled up with steel fibers are highly conductive. So what will happen to the rapid chloride penetrability value? It will increase. You have a very high rapid chloride penetrability when you test steel fiber concrete. Similarly, when you test geopolymer concrete, which have a lot of alkalis, sodium, potassium, obviously you are going to get a very high value of rapid chloride permeability, even though the true durability of that system may be much better, but your RCPT value is very high. Okay, so there are several disadvantages. You need to keep that in mind while conducting this test. So based on the disadvantages, people have proposed other test methods which are more well developed and which give more quantitative classifications of the concrete. One is called the accelerated chloride migration test, which is in principle quite similar, but here what you do is you do not apply the same potential difference of 60 volts to all concretes. Based on the resistance of the concrete to current flow, you apply different levels of potential. For example, for concrete that allows a lot of current to flow, you apply a smaller potential, okay, so that the concrete specimen does not get heated during the test. And using this test, you get a very clear migration coefficient, and that migration coefficient can again be related qualitatively to the concrete quality. But here please remember, since you are getting a migration coefficient, you can now use it in models that use coefficient of diffusion to predict the life of your concrete. So that is the advantage of the rapid chloride migration test, accelerated chloride migration test. Okay, so here what you are doing is, after the passage of the electrical potential for a given period of time, the test can take sometimes 2 to 4 days. You split open the concrete and measure the depth of the chloride penetration. How do you measure depth of chloride penetration? On the fractured surface of the concrete, you spray silver nitrate. You have learned this equation in your basic chemistry, that silver nitrate, when it reacts with chloride, forms silver chloride, and that gives a white precipitate. So you can actually see to what depth your concrete has been penetrated by the chloride, and that gives you a direct measure of the penetrability or resistance to chloride penetration. That is why this test is a lot more preferred as opposed to the rapid chloride permeability test. You can also directly measure the conductivity or resistivity. You know that concrete will be more resistive to the passage of electricity if the pores are not connected. Okay, in other words, a concrete that is less permeable will be more resistive, and vice versa, a concrete that is more permeable will be more conductive. Okay, so by measuring resistivity or conductivity, you can actually test the permeability indirectly for the concrete, and these tests give you very nice indication very rapidly. Okay, so there is one test called chloride conductivity test, for which we use the same type of specimens as we used here in water sorptivity and oxygen permeability test, the same 69 millimeter diameter and 30 millimeter thick slices, and here the slice is completely saturated with sodium chloride, and then you put it in a conduction cell where you apply a potential difference. So now what is going to happen, you are going to simply measure the conductivity of the concrete, because there is no diffusion happening, there is no migration happening, because all the sides of the solution, all the sides are saturated with respect to sodium chloride. In the case of RCPT, please remember, one side had sodium hydroxide, the other side had sodium chloride. Here everything is saturated with sodium chloride. So all you are measuring is the conductivity of the concrete itself, and this test takes only 5 minutes to conduct, and you get a value called the conductivity, again can be related qualitatively to the category of concrete, very good, good, poor, or very poor. So again, very rapidly you get a measure of how good your concrete is. You can use this for cores that are taken from the site also. One thing that is increasingly gaining popularity everywhere is simply a measurement of the resistivity. Now in soils, there is a 4-probe test to determine the resistivity of soils. That same concept has been applied here in the Wenner 4-probe resistivity test. So here you have the Wenner probe, it has got 4 different electrodes that are kept in contact with the concrete. You apply the current across the 2 outer electrodes and measure the potential difference between the inner electrodes. Okay, and that potential difference is converted into the resistivity of the concrete for this type of a measurement. Okay, and that resistivity you can then relate to the concrete quality once again, and this test takes you probably about 1 minute to conduct, because it is such a simple test, very quick test. Only thing is, it is highly sensitive to the moisture conditions. If you have wet concrete, it will give you very low resistivity, because obviously if you have more water, the water inside the pores will make it more conductive. If you have dry concrete, if there is no water inside, even if you have a permeable concrete, if there is no water inside it, how is the conduction going to happen? It is not going to happen. Okay, the more wetter the concrete, the greater the conduction. So any moist concrete will affect the resistivity. So you need to do it in a very controlled condition. So if you are testing resistivity of concrete, you have to maintain the same condition throughout the test. It should always be moist or it should always be dry. For conservativeness, we always want it to be moist because that is when we get a lower value of resistivity. And please remember, as I said earlier, more resistive the concrete, the less permeable the concrete. In other words, higher resistivity means a better resistance to penetration of liquids and better resistance to corrosion. Higher resistivity, better resistance to corrosion. Okay, I'll just quickly wind up with some results from IIT Madras for all these different types of tests so that you get an idea. So I have given you some examples here of effect of mineral admixtures like fly ash and slag on concrete resistivity. So here you see again the lines pertain to the classification of the concrete, like this classification that I talked about here, the same lines are being used here. So this is very poor, poor, normal and good. You can see that the ones which are normal and good have a very high proportion of slag and fly ash replacement. So when you replace cement with slag and fly ash, your resistivity increases. That means the potential to resist the flow of ions and water inside the concrete and resist corrosion increases when you replace cement with fly ash and slag. Effect of curing duration, you know that sometimes when you use fly ash and slag the hydration is slow. So you can study that by the help of concrete resistivity, and here you see that the incremental enhancement of resistivity from 28 to 90 days. So curing was increased from 28 to 90 days, the incremental enhancement in resistivity is maximum in the case of fly ashes. You see here these are all data for fly ashes. You have major increase in resistivity from 28 to 90 days. In other words, it tries to tell us that the greater you cure concretes with mineral admixtures, the greater will be their contribution to the durability of the system. Now this is chloride ion penetrability measured by RCPT. As I told you, 2 to 4000 is moderate, 1000 to 2000 is low, 100 to 1000 is very low. So you see here that when you use greater contents of slag and fly ash, you are coming to the low and very low chloride penetration. That means very high resistance to chloride penetration when you have fly ash and slag. Again, this is by the accelerated chloride migration test. You get lower and lower values of migration coefficient when you substitute cement with slag and fly ash. That means you have much more improved performance. And this is the chloride conductivity test. Once again, for the levels of replacement that are large, you get very low conductivities through the concrete. That means you get an excellent behavior of the concrete. Again, water penetration with increased level of substitution of cement, you get much lower water sorptivity. This is depth of water penetration, not sorptivity, sorry, depth of water penetration in the DIN 1048 test. Okay. In the case of sorptivity also, you get much better performance when cement is replaced by mineral admixtures. This is the accelerated carbonation test. Now one thing where mineral admixtures don't always perform as well is the carbonation resistance, because now when mineral admixtures are there in the as a cement replacement, they are actually eating up your calcium hydroxide. Now because of that, the buffer that you have for carbon dioxide penetration, that is calcium hydroxide, is reduced. So as a result of which carbon dioxide will penetrate deeper in concretes that have mineral admixtures. So here you see the effect of replacement of mineral admixtures is generally to increase the depth of penetration of carbon dioxide. So carbon dioxide penetration depth has increased with increased replacement of cement by fly ash and slag. Again, oxygen permeability, you don't see too much differences. Okay. So one quick note about correlation between durability parameters. Again, you can actually correlate many of these parameters, because please remember in many of the tests we are actually measuring the conductivity or resistivity. So obviously those are related. In some other cases we are measuring water sorption and water penetration. So those are not related. So let's see which ones get related nicely and which ones are not. So this is the accelerated chloride migration test, migration coefficient against the Venner resistivity, and you can see there's a very strong correlation there. Why? Because accelerated migration is testing some sort of a conduction through the concrete, and resistivity is measuring the opposite of conduction, that is resistivity. So there has to be an inverse relationship between the two that is very clearly captured in this case. Same thing between Venner resistivity and rapid chloride permeability, because they are measuring opposite but the same mechanism, but just the opposite they are measuring. Now this is depth of penetration by water permeability test method where you apply a pressure and cause the water to penetrate, and this is sorptivity by capillary action. Please remember we discussed earlier that these are very different transport mechanisms. So obviously you do not get a good relationship between these two because they are measuring two very different transport mechanisms, okay. So this clearly tells you that test methods should be related to the transport mechanisms, only then you can make good sense out of it. One important characteristic to understand is strength need not be related to durability. You see this data here, it plots the compressive strength against different durability parameters and you do not get any good relationship at all. So there is no correlation between strength and durability parameters. In other words, you can make low strength concretes also durable if you choose the right blend of cementitious materials. Okay, so that brings us to the end of this lecture module on testing of concrete. I will take a few questions to finish up the session, but I also wanted to tell you that you can visit this website www.theconcreteportal.com, and this website has several of my lecture notes presented in different segments. I have talked first about the concrete fundamentals, and then there are special advanced topics which are based on the kind of research that we are doing here. So you will probably be able to get a lot more information about durability, about different types of tests and so on from this site. But of course the site is only meant to be an addendum to a textbook. So I prescribe that you should buy a good quality textbook if you are interested in concrete technology. Personally, I would suggest the Properties of Concrete book by Adam Neville as the best book to purchase. Otherwise, I would suggest you should go for the book by Mehta and Montero. Okay. So both these books are available in Indian editions for relatively inexpensive prices. I suggest that you at least have one of these as a ready reference if you want to learn a lot more about concrete technology. Okay. So thank you all very much. It's been a pleasure interacting with you. I'll close the session with a few questions from you. Whatever you may have, please do let me know. Okay, so we have a question which has been raised which says why we prefer rounded steel bars and reinforcement instead of rectangular or square shape. That's not necessarily related to what we are discussing here, but still please remember that a lot of the steel usage is related to the kind of processing that you have, and it's much easier to process a rounded bar as opposed to a rectangular or square shaped steel bar. Okay, further what happens when you have a rounded bar is that you avoid stress concentrations at the edges. When you have square or rectangular bars, because of the sharp corners you may have some stress concentrations which may lead to defects and failures much before your tensile strength limit is reached. Okay, so again that may affect the performance. How we can maintain neutral level of pH level of water in marine construction? Now again please remember, marine construction is still happening with water that is supplied to the job site, and this water that is supplied to the job site has to be of the right quality. You can't use seawater for construction. For construction or for the preparation of concrete, you will be using water that is supplied from the mainland. Okay, that water has to be potable, free from chlorides, free from sulfates, free from alkalis, with a more or less neutral pH. The seawater is the environment that the concrete is going to be suffering in its long term after it's hardened and gained sufficient strength. Until then you need to protect it by providing water for curing, which is also from the mainland, which does not have any salt in it. Okay, so that water has to be well controlled with respect to its pH. How types of fine aggregate affect strength of concrete? Okay, now of course I guess the question relates to the use of river sand versus manufactured sand. Okay, because now we know that there are several sources of sand that are depleting. River sand is depleting, so people have started looking for alternatives to river sand. One of these alternatives is to crush coarse aggregates and make it finer. So the fine aggregates that you get from crushed coarse aggregate are bound to be a lot more angular, and sometimes if you don't use the correct equipment, they are bound to be a lot more flaky as opposed to the rounded aggregate that you find in river sand. So sometimes they may affect the water uptake and create a greater demand for water to produce the same workability in the concrete. So obviously if you have more water, your strength is going to suffer. Now if you use the appropriate chemical admixtures to keep the water content constant, then the strength may not be affected by the use of crusher sand. Sometimes because of the angularity and the better packing that you get with crusher sand, you may actually get higher strengths also, but it is not a guarantee, okay. So for the most part, by increasing water demand, you are going to be reducing the strength of the concrete. Question, why fly ash is used in manufacturing of cement? Fly ash is used in the manufacture of blended cement, Portland pozzolan cement, in which part of your cement is substituted by fly ash. What are the benefits? One major benefit obviously is the reduced heat of hydration. You know that when cement reacts with water, it liberates a lot of heat. So you can reduce that heat by substituting cement by a lesser reactive material like fly ash. Other advantage with fly ash is the reaction of fly ash proceeds for a very long time. That means the concrete continues to evolve and develop its structure over time. And third advantage is that the presence of fly ash leads to better chloride binding and improves the durability in seawater or marine conditions. Even in normal concrete conditions, the permeability of the concrete is reduced significantly when fly ash is used as a substitute for cement. So that is why we want to use fly ash in concrete. Okay, so I guess most of your questions have been answered, I hope. And as I suggested earlier, please have a good textbook with you so that you can get a ready answer to most of your questions that you have in concrete technology. Of course, durability test methods may not be adequately covered in several of your textbooks, and special categories of topics like rheology, which are getting increasingly important nowadays, may not be something that you'll find all the time in your textbooks. But anyway, you're welcome to interact, and you can send me email. You can find my email from the IIT Madras website, and you can send me email if you want to interact further and get to know some more answers based on the content that has been presented here. I wish you all the best in your future studies, and thank you all once again.